We're very fortunate to have Iason Baldes. You already know him because he was here last week too. As a very attentive student. I was taking notes of everything. So Iason, he did his PhD at the University of Melbourne in Australia. And has a postdoc at DESY. And then he went to University of Brussels. And currently he's at the École Normale Supérieure. So thank you for accepting our invitation. And I think you're going to talk about asymmetric dark matter, right? Thank you, Iason.
So thanks for the invitation. And I was told to talk about alternative scenarios. And the suggestion was asymmetric dark matter, which I've worked on quite a bit, and Affleck-Dine baryogenesis, which I've never worked on. So then I took the alternatives as an invitation to to talk about whatever topics I think will be helpful and that I can explain well. So the plan is lecture 1 will be either, for some of you, a review, for others, hopefully a good introduction to symmetric dark matter freeze out. So this is a well-known example in the literature. It's been studied a lot. It's a standard technique, so I thought, for the students who haven't seen it before, it'll be useful to have a look in somewhat more detail. And you can actually solve the Boltzmann equations to a very good approximation analytically. So I hope to show you that today. And then lecture 2 will be asymmetric dark matter freeze out. Okay? And this is just follows on nicely from the initial topic. So for symmetric dark matter, I mean dark matter where the number density of dark matter particles equals the number density of anti-dark matter particles, or if it's a Majorana fermion or real field, then of course there's no distinguish. Yeah? While for asymmetric dark matter, we'll have the situation where, in general, say, by definition, the number density of dark matter particles can be larger than the dark matter density of the number density of dark matter antiparticles. So then, in these sorts of scenarios, the abundance of dark matter today will be set in a way similar to the abundance of visible matter. So for this reason, because we know so little about dark matter, it's an interesting scenario to consider. And the third lecture will be sort of asymmetry generation for asymmetric dark matter. So there, in principle, you have a lot of different possibilities. So you say you assume that at low temperatures today, we have this situation, just like in the visible sector. You have more particles than antiparticles also in the dark sector, and then there's a whole range of possibilities for generating this asymmetry. And some of them lead also to unique low energy phenomenology. So this will be the topic for the third lecture. So I'll give then some simple scenarios. And maybe the whole thing might take 4 lectures instead. So then the fourth lecture could be, if we have enough time, is going to be a tutorial on how to calculate of CP violating decays. Now, I'm not sure how much Torma will go into detail in the context of leptogenesis, but if he discusses this in detail, then I can change the plan again. But I think it'd be useful, if we have enough time, to show you how to calculate extract, in terms of the underlying parameters, the amount of CP violation in a decay, because this comes up a lot in studies of baryogenesis, and it requires some technical tricks that can be very useful and so worth looking at. So then, on to the first topic. So we want to study now the freeze-out of symmetric dark matter. So we also heard about this a bit from Shaposhnikov last week, but now we're going to look at the Boltzmann equation in a bit more detail, okay? And there's going to be a number of assumptions that go into this. Yeah? So, of course, I already told you the first one is that we have this equal number of dark matter particles and antiparticles, or if they're indistinguishable. The second assumption that we're going to make, or I wrote first assumption here, but is that the dark matter particles are in kinetic equilibrium. Okay? And that means that the number density we can describe in terms of the phase space density, where this is in general a function of the 3 momentum, but in kinetic equilibrium, in the plasma frame, this just becomes a function of the energy, and we have the standard relation. Okay, where minus is for bosons and plus for fermions. Okay, and then using the standard relation between energy, momentum, and mass, you can see that rewriting this integral in terms of the energy, you'll see that for large temperatures and 0 chemical potentials, that the number density is given by zeta 3 on pi squared g. G just is a degeneracy factor. It just counts the number of degenerate particles. Yeah? So just the number of degrees of freedom of this particle that's being with the phase space density F. So for bosons and for the opposite statistics, you just have a factor of 3/4 here. Okay. And then in the opposite temperature regime, which is where, for reasons I'll go into, the symmetric dark matter freeze-out occurs, we'll have N being Boltzmann suppressed. And now it doesn't depend on the, okay. Now it doesn't depend on the, this is, M on T, and now it doesn't depend on the statistics we use. We can ignore this factor here. Okay. This is if the particle has 0 chemical equilibrium. Yeah? For dark matter freeze-out, we'll be interested in this regime where this phase space distribution will be able to take using Maxwell-Boltzmann statistics. So then f of E will just be e to the negative e on t and e to the mu on t. Yeah? So if there's, and here in principle, if you have a chemical potential, you'd have a mu on t as well. Okay, so we'll be in this simple regime where the phase space density of our dark matter will take this form here. Yeah. So all the departure from thermal equilibrium will eventually come to a rescaling of the overall phase space factor here, compared to the case where there's zero chemical potential. Okay, and now you might ask, is this a good approximation to make this of kinetic equilibrium? And in a lot of cases, it's actually a good assumption, right? And the reason is the following. So we're interested in dark matter freeze-out. So we're interested in some situation where dark matter particles are annihilating. In the simplest cases, in a 2-to-2 process. So let me call this, let's say, psi standard model bar. And when this freeze out is occurring, the temperature is far below the dark matter mass. So the number density is sort of suppressed. Yeah? While the number density of the plasma, which here we'll assume to be the standard model plasma, the number density there will have plenty of radiation. This is happening in radiation domination, so you'll have plenty of degrees of freedom with this sort of distribution. So the number densities are much larger than the dark matter number density. So then it's sort of often the case that scatterings which keep the dark matter at a common temperature with the plasma these are occurring much more rapidly than this process. Yeah? Just because here you have a standard model particle in the initial state whose number density is not suppressed. Okay. Now, as we heard last week already, we'll be interested in the situation where, just to give a very rough approximation, right? So the annihilation of these dark matter particles, the annihilation rate is just given by the number density. So if you, let's say we're tracking the number density of X particles. The annihilation rate of X particles will depend on the number density of X bar particles, because that's what they see. Yeah? But because we're considering the symmetric dark matter case, this is just the same number density. And this rate, this is the thermally average cross-section. I'll give a more detailed description of it during this lecture. And when this annihilation rate drops below the Hubble rate, this is when these sort of annihilations will stop. And then afterwards, the number density of dark matter particles will just be set by the expansion of the universe. Yeah? So then after this, if you normalize to entropy instead, Yx, Nx over S, this will be constant, yeah? As long as there's no entropy production afterwards. So that's the basic picture. This is the rough approximation, and now we'll look at the Boltzmann equations in more detail. So now we want to track this abundance of X.
What? Someone has questions? All right, go ahead.
Yeah. Okay. Now we want to track the number density of these X particles. Now, first of all, consider, just to give some intuitive picture, what's happening when there's no interactions, so when there's no annihilations, right? So then the number density Nx is just given by some constant divided by the scale factor, yeah? So if normalize the scale factor R here to 1 today, this will just be the number density today, yeah? Divided by the scale factor cubed, okay? So then what happens to the time derivative? Okay, it's just very simple. This is just equal to negative, so you take, this is constant, you take the time derivative, you get the minus 3 nx naught r to the 4 dr dt, okay? And this is just dr dt divided by r, the scale factor, this is just h. Yeah? So we'll just get negative 3 nx times h. H is the Hubble rate. H is just r dot on r. Okay. So very good. So then, if there are no annihilations, right, then these two things are equal. So let's just take this on the left-hand side, and then we'll have a relation okay? And so often you see this form, it just means that there's no annihilations going on, changing the number density. So, let's write after freeze out, or well after freeze out, yeah? So now we want to take annihilations into account. So now we're going to include the annihilations. So we have interested in the time derivative again. We include this factor, which is taking into account the expansion of the universe, diluting the particles. And now I'll write down the collision term. I'm not deriving it. I'll just give you the correct normalization and so on. So we're going to sum over spins. This is going to be with a minus sign here, so we'll be first removing particles. So it's an integral. Let's say we're going to label our particles for our annihilation. I'll give them labels 1, 2, 3, and 4. So this will be like F1, F2, so it depends on the initial phase space densities. Now, in general, it will depend also on the, if quantum statistics are important, it will also depend on the final state, Bose enhancement, or Pauli blocking factors. So I'll just start off again with having these quantum statistics, and then soon we'll get rid of them. Then it depends on the matrix element squared of this process, which you could say find from quantum field theory. And then you have the reverse process, yeah? Okay. So now we want to close our brackets here. So this is the process that's removing particles from this phase space, the annihilation, and this is the reverse process, going in the opposite direction, creating dark matter particles again. Okay, and then we have to integrate over these phase space densities. So now this sort of integration measure appears over and over again. So we'll just label this like this, so shorthand notation. So we integrate over our dark matter particle phase space density, the antiparticle it's annihilating with, and the outgoing phase spaces. Okay, so it's sort of a bit scary looking formula, right? But don't worry, now we'll simplify it. Yeah? Okay, and notice that because of this assumption of kinetic equilibrium, we can use this so-called integrated form of the Boltzmann equation, where we're tracking this overall number density rather than having to track the individual, phase space density itself, right? That's a much more difficult problem to solve. Okay. So now, we said we can go into this low temperature limit where the temperature is below the mass, and we can use Maxwell-Boltzmann distributions, okay? And to see this, and yeah, you just examine this phase space distribution. Sorry, I missed the divided by temperature here, okay? So you look at this phase space distribution and you see, the energy is going to be at least the mass, yeah? So then, and the chemical potential is going to be small, 0 or small, yeah? So then this exponential is always much larger than 1, yeah? So then you can get rid of, use the Maxwell-Boltzmann statistics there. And so these terms here, we can ignore, yeah? Okay. And here, these are the phase space densities of the standard model particles. With energies, when these dark matter particles annihilate, the standard model particles also have a significant energy compared to the temperature. So we can also ignore the quantum statistics. And in particular, you might think, okay, maybe these final state particles have some chemical potential. Yeah? But these chemical, this is going to be like annihilating into the standard model plasma, where any over density in F3 and F4 gets reprocessed into the thermal bath, which has like 100 and something degrees of freedom. So it's and the interactions are very rapid, say the gauge interactions. So then we can also ignore that there. So we already then simplified quite a bit. Okay. Now, yeah. So this was sort of, let's say, assumption 2. Assumption 1 was kinetic equilibrium. Assumption 2 was Maxwell-Boltzmann. And assumption 3, we can separate it a bit, is that mu3 and mu4 approximately 0. Okay. Okay, and now there's a little trick. Let's define F with an equilibrium at the top, just to be the phase-space distribution without a chemical potential. So F with mu equals 0, okay? Then, n equilibrium will just be n with mu equals 0, yeah? Now, look at this term here, F3, F4, yeah? And we said that mu3 and mu4 are 0, so we can write here equilibrium. Yeah? Now, this factor is nothing else than e to the minus E3 plus E4 on the temperature. Okay? But notice we have this delta function here enforcing form momentum conservation, right? So under the delta function, you can just replace this with negative E1 plus E2 on the temperature, which is just F1 equilibrium, F2 equilibrium, okay? Now, under the integral sign, yeah? Now, so basically this is going to turn into F1, our dark matter density in equilibrium, F1 equilibrium, F2 equilibrium. And now we still have this matrix element, which is the time reverse process, right? Instead of 1, 2 to 3, 4, you have 3, 4 going to 1, 2. Now you can either assume in many of these scenarios of dark matter annihilation and freeze out, you'll have time reversal invariance. Yeah? But you don't even need to do that if you imagine that we sum over the final state. So basically, we want to replace this matrix element squared with just this one. And obviously, you can do it if CP is conserved. But even if not, imagine what you're interested in finding the dark matter number density is the sum over all possible final states. And then I won't talk about this in detail, but there's a result that says then that the matrix elements are, when you sum over all the final states, they're related this way. Okay, so this is just a little detail. It's not so important because you could also just, in this simple scenario, you can just assume CP invariance. So then putting all this together, let me write it here. So now we'll write out our Boltzmann equation again. With all the simplifications we've made. I should mention, yeah, this integral sign here, you have lots of integrals to do in principle, yeah? This just represent, should write many, many integrals here. So, F1, F2, minus F1 equilibrium, F2 equilibrium, and our matrix element squared for the dark matter annihilation. And then we still have the properly normalized Dirac delta function. And a reminder of all the, this should be, there's so many integrals I ran out of space, you see. Okay. And now we can do the, see here, these equilibrium number densities, okay, just depend on E1 and E2. All these things just depend on E1 and E2. So we can do these phase-space, these final state phase-space integrals, yeah? So what we want to do is basically we want to evaluate the sum over spins. Two, 3, 4. Yeah, okay. Okay, I should say, I'm doing this for simplicity with a two-body final state, but in generalizes very straightforwardly, okay? Now this integral, you look in your textbook, and you'll see that this is just simply related to what you know about annihilations or scatterings in quantum field theory. So this is just related to the usual cross-section that you know. Okay? And because we've summed over spins, we get a factor G1, G2. Okay. Yeah, usually, okay, this matrix element by assumption is the sum over initial spins and average over final spins. Now you sum over all the spins, and you get a G1, G2 factor because it's not, we haven't averaged, yeah, okay. Sorry, this is just the sum over all, yeah, but here, okay. Okay, so now, now we have this result, and now yep. The G and the sigma, yeah, that's a very good question. I almost forgot to say this is very important. This is the Muller velocity. So basically, yeah, this should be, yeah, this is to distinguish it from the relative velocity, okay? So this is the standard flux factor appearing, yeah? And it's by, we won't necessarily have to use this full form in detail, yeah? But I just write it down so you see the definition. So in terms of the form momenta, it's given by this factor. Minus m1 squared, m2 squared. And in terms of particle velocities, it's given by the square root of V1 minus V2 squared minus a cross product between the velocities. Okay. This is what it is in detail by definition, but we don't have to use this form later on. No. So in principle, if you do this, if you take this matrix element from QFT and you do the final phase space integral, you get this factor here. And then you have to be careful because in some textbooks, they just write this part because they're thinking about some collider experiment where the beams are head-on. You can look in the textbook by Mandel and Shaw. Okay, for example, it's explained. Okay, now we'll define N1 equilibrium, N2 equilibrium, and then the thermal, this is by definition of the thermal average cross-section. This will be G1, G2, sigma V Melaire, and F1 equilibrium, F2 equilibrium, and then D3P1, D3P2. Okay, so you have still a 6-dimensional integral to do here, principle. Okay, but this we'll calculate this later. It'll simplify a lot. Yeah? Okay, so having made this definition, we see here we get this when we do this final phase this integral over these final phase spaces. We see we get this cross section here, okay, and you see here this 4 E1 E2 sort of cancels off some 2 E1 2 E2 factor. Sorry, I forgot here. This should be, you should still have 2 pi cubed factors here though. Okay. And then you see this factor here, if you just focus on this second term here, the inverse annihilation process, you see this thing here is just going to give us this factor with these equilibrium number densities. When you integrate over, because of these here, that appears here. Okay, and so that's one thing, and then the other factor here, F1, F2, remember is just equal to E mu1 plus mu2 on T, F1 equilibrium, F2 equilibrium. So it factors right out. Yeah. So now you'll get a factor here. Here you'll rewrite this with equilibriums here, and then you just have these mu1, mu2, and so then everything can be rewritten in a neat form. I should say the notes are also, a scanned version of the notes is also posted on the website, so if you are worried about some typo or something, or you want to work through some steps, you can also find the notes there, in addition to whatever notes you're taking now. Okay, so then using this definition of the thermally average cross-section, we just end up with an equation So it has a very intuitive, you can get a very, you can get a very intuitive feel here. This is just the number change of x due to the annihilation process. Depends on the number densities of the particles, and then also the reverse process, which is set by the equilibrium number densities. So if this annihilation cross-section is large, these number densities will be driven towards the equilibrium values. Now, here I've written everything in terms of distinguishable particles, x and x bar. Yeah? So then, for distinguishable particles, you'll also have another Boltzmann equation, which will just be with, instead of x here, you'll have x bar, and so on. So you don't have to solve it twice, though, but you'll find that your dark matter number density will just be nx plus nx bar equals to nx, yeah, at the end. Now, for indistinguishable particles, x bar. Here, what will happen is that each annihilation now removes 2 of these particles, yeah? So you get a -2 sigma v mol nx squared minus nx equilibrium squared, okay? But here in this, it's convention that when you take this thermal average, you don't put a factor of 1/2 when you do the phase space integral over indistinguishable particles. Yeah? Like when you calculate a cross-section, if you have identical particles in the final state, you can't double count. Yeah? So, but here by convention, you don't do this. So there should be also a factor of 2 here, and these things cancel. So then in the end, it's sort of, by convention, it makes things, let's say, a bit simpler because you can just solve the same equation with all the same factors. But in the case of distinguishable particles, you'll just, whatever number density you'll get in the end, you'll just multiply by 2. So the Boltzmann equation is the same for both cases. Okay. Now, as we already heard lots of times, it's useful to instead go and write instead the number density normalized to entropy, okay? Where S is the sort of the conserved entropy divided by the volume, and it's given by 2 pi squared on 45 G star, and factor counting all the degrees of freedom, the effective number of degrees of freedom for the entropy, times T cubed, okay? And this will be our assumption 4 is going to be no entropy production. Okay, during or after the freeze out of the dark matter particles. Yeah, you could have some entropy production earlier, and it won't matter, but otherwise you'll shift this value. Okay, so David also had a question last week about, we're assuming here always, radiation domination. The dark matter density is set, but there's still a lot of radiation around. Okay, in this scenario, the dark matter density will be set, let's say, at temperatures above 1 GeV, just to give a typical value. Could be higher. And then you still have a lot of radiation around until the time of matter radiation equality. To get the correct cosmology out, you'll have until temperatures of 0.8 electron volts or so. Yeah. So, but of course, you can go to a BSM scenario which has an epoch of early matter domination, right? And then you'll change your Hubble rate. You'll change your, and then if you have some late decaying particle, you'll have, before entering into radiation, you'll also have some entropy production, or you can have a phase transition. So, sorry, Thomas, no phase transition here. It's just crossovers, okay? Okay. So then, yeah. Now, ds/dt, you have this volume factor here, which just goes as r cubed. So again, you'll have various relations, such as ds/dt is -3 times h times the entropy. And then you can just do a change of variables, right? So here we had dnx dt, and now you just do a change of variables and find dyx dt. And you should find, okay, it's just a simple, I leave it as a little exercise if you want. You should find that this is just equal to sigma v over s, nx, equilibrium, minus nx bar. Okay, I just switched this and got rid of the minus sign. And then, and so this is just equal to s times sigma v, yx equilibrium squared minus yx bar. So okay, I didn't do all the little steps in between, but it's really just a change of variables. Yeah, it's very simple. And similarly, using the definition of the Hubble parameter 1 on r. R is the scale factor here. dr dt equals h. You'll find that then you change variables in terms of the, now we have the time here, now we change to the scale factor as sort of our time coordinate. And you'll very simply find that this is just h yx equilibrium squared minus yx bar. Okay. Now the next step's also straightforward change of variables, so I'll leave them as an exercise, but I'll give you the idea just so that we save some time. It's really just using like a chain rule and so on. So just in the interest of time, you just now we want to change coordinate. We have here the scale factor. Just change to what I call x, which is just the dark matter mass over the temperature. This is a standard thing. Use this, and also that you can use d dx SR cubed equals 0, and you can evaluate in some way you'll have to evaluate, find what ds dt is. Sorry, ds dx. So then you can do change variables to this x. So I leave that as an assumption. As an exercise. All the steps are in the notes. Yeah, if you get tripped up for whatever reason. So assumption 5. We'll also use assumption 5, which is that we're in a radiation-dominated universe. And so that h equals root 8 pi on 3 square root radiation density over m Planck. And rho rad is just g star radiation pi squared on 30 t to the 4. Okay. Okay, there can be, once the neutrinos have decoupled, there can be differences between G star S and G star R, but for our purposes here, it's not so important. I just include them so that it's more general. Okay. So then, putting everything together, we get a very useful form of the Boltzmann equation that dyx dx, d little x, is equal to negative pi on 45 m Planck m on x squared. Then you have this factor, which I'll write out, 1 plus t on 3. This factor comes from the ds dx that you'll evaluate as an exercise. G star s dg star s dt. So this is only important when the degrees of freedom are changing during the freeze out. Okay, it's important when you do a numerical calculation if you're interested in a lot of precision, but for us it's not so important. And then you have a factor of here g star. Let me write it here. 1 on g star radiation to the 1/2. Okay, and then I'll define all of this factor here. I'll define all of this as just G star S tilde on G star R to the 1/2. Okay, so at very high temperatures, where all the standard model degrees of freedom are massless, effectively, then this is like a factor of 10 or so. Yeah, because the G star is like 100. Okay, and it's also useful that sometimes different conventions are used. This is the full Planck mass, not the reduced Planck mass. So it's like 1.2 times 10 to the 19 GeV. I just write it down so that otherwise you have to go back and figure out, did I use the reduced Planck mass or the full? Okay, so this, and then what did we forget? We forgot the M Planck M then we have, again, our thermally average cross-section. I set now the number densities of the dark matter equal, and so, okay, very good. Okay. So now I have to be a bit quick in the interest of time. So, okay. So I'll just sketch here how to find a useful formula for the thermal average sigma V. So a lot of the details are given in the notes, and a useful reference would be, say, this paper by Ezio and Gondolo. It's from 97, okay? Okay. So let me just, this take a while to do in detail. So I'll just give a sketch and then give you a useful formula, and then you can go back if you're interested in deriving it and so on, yeah? And if you're not interested in deriving it, you can still use the useful formula and just trust clever physicists. Yeah. Until you get some time to derive it yourself. Okay. So the point being is in this thermally averaged cross-section, there's an expression, there's this sort of crazy-looking integral 6 there. Then you have something like, this factor we found, and then you have the distribution functions of the initial states. I just label these initial states I and J here, yeah? So then there you have the full, here we reintroduce the energies from here, E, I, E, J. Okay, D3 Pj to 2 pi cubed 2EJ, okay? Then this is the sort of integral you want to get into a useful form. And in the end, it will collapse into a single integral, which is very easy to estimate or evaluate numerically. Yeah? So there's a whole procedure, how to do it. You can see that, you want to do some clever change of variables, which is like, there's a clever change of variables involved, like you use different energies, and also you change variables to S. This is the Mandelstam S, the center of mass energy squared. So it's equal to this, Pj cos theta, and this factor here, sigma v, this whole thing here actually just ends up depending on S, which allows a lot of simplifications. So when you do this, rewrite everything in terms of these new variables, find the regions of integration. Then you find that, now I'll just skip ahead. So there, I gave I'll just give the useful formula, which isn't just useful for dark matter freeze-out. It can be useful in applications of baryogenesis from decays and scatterings and so So in whole different context, yeah. So in the end, okay, and I'll even give you a more general formula where the masses of the initial state particles can be different, yeah. So in the end, the full thing, you know, we've assumed Maxwell-Boltzmann distributions, of course. This factor here is just given by Gi, Gj, T on 8 pi to the 4. And then you have one single integral to do instead of 6. So you can be very happy that Gondolo and Gelmini and Edzo and Gondolo, you know, sweated away in deriving this. Okay. You have the center of mass momentum appearing here. The initial state energies, sigma v mol. This you'll just find from, this factor here you'll just find from QFT, say. And then you have here a Bessel, a modified Bessel function appearing. Basically, this takes into account that, you know, when you have these distributions, that when you know, if your S, your center of mass energy squared, gets very much higher than the temperature, there are a few particles around that can scatter at such high energies, at energies much higher than the temperature. And this gives you effectively a suppression here of this thermal rate, okay? Okay, and then these factors here, yes, sorry. Yeah. Where did I drop that? My notes. Sorry, thank you very much. So, yeah, this is going to be a function of S. Okay, so now in one, okay, basically, yeah, in I equilibrium is also going to be given in terms of a modified Bessel function, and it's just m squared t on 2 pi squared k2 m on t. Okay, and you can see, okay, this is just the this is the full expression for Ni equilibrium in the approximation of Maxwell-Boltzmann statistics, but for all temperatures, yeah, even where the Maxwell-Boltzmann statistics, strictly speaking, aren't valid. But this, if you expand this out for large arguments, you'll find exactly the same form of the number density we had earlier, yeah. So then, yeah, so then in okay, and let me, yeah, I should give this. In full generality, here this PCM squared is given by the factor, let me write it out. This is a standard form. Squared S minus mi minus mj. So if you're doing, say, some numerical evaluation, yeah, you could just substitute this in and evaluate the thermal average numerically, but we'll see there's some useful analytic limits as well. Okay, so that's PCM squared. Okay, good. Okay, now we'll go back to our, so this is sort of just a useful formula which appears in all sorts of places in the interplay of particle physics and cosmology. So now we'll go back into the non-relativistic limit. Okay? With mi equals to mj again, equals to mx. Okay? In that case, PCM squared is 1/2 root s minus 4mx squared. Your EI and in the center of mass frame, these are approximately mx, and s is equal to 4mx squared plus mx squared v rel squared. Okay, there'll be a correction here due to the relative velocity between the dark matter particles. I could just miss this factor, so let's just keep it with s here. Okay. So, yeah. And these factors, this is root pi t on 2 root s e to the minus root s on t. I shouldn't have deleted those. Yeah. So at low velocities, at this point, we'll just use this approximation that the energies are just the typical relative velocity at freeze out is like 0.1 or so. So the energies are dominated by the rest mass. Okay, and K2 m on t. So these were the different factors appearing there. This is approximately root pi t on 2m e to the minus m on t. Okay, and then you should find that, and using x equals m on t, then in the non-relativistic limit, where we can replace the non-relativistic limit, we can replace also sigma v molaire with sigma v rel. Okay, and we can go into the key point here is in this non-relativistic limit, we can go into the center of mass frame, basically, and everything is the same. Yeah. Okay. Yeah. Then in this non-relativistic limit, we can go into the center of mass frame instead of the plasma frame, and then we can use this relative velocity. Yeah. And then sigma v rel can be computed in the center of mass frame. And also, we'll see because of that, a useful expansion in terms of v rel is possible. Sorry. Let me mention one thing before. Sorry, I skipped ahead a bit. In the non-relativistic limit, okay, we don't now. This thing, which we can still, we'll keep the sigma v molaire for now, but this changes then. This formula here changes into an integral over the relative velocity. E to the minus x v rel squared on 4. Okay, so this is just a rewriting in this non-relativistic limit. And then for analytic approximations, it's useful to expand sigma in terms of relative velocity instead of molar velocity. And you can do this in the non-relativistic limit. It comes out the same, okay? This is discussed a lot there's a reference in my notes, it's discussed a lot in a paper by Gondolo and Gelmini in an old paper. Okay, so then we can write sigma v rel as some sigma and then v rel to the 2n, okay? And this comes about through a expansion in partial waves of the total angular momentum. So there's basically, depending on the underlying model, there's some interesting behavior. Okay, so if n equals, you can have a situation where n equals -1/2. So that this is a feature of, this occurs when the effective interaction becomes long range and Sommerfeld enhanced. Okay, so and then there are other scenarios, say if there's a contact type interaction with the total angular momentum 0, the leading term goes with n equals 0. And if it's p wave, j equals 1. This is S wave, contact. And this is P wave, contact. This Sommerfeld enhanced enhancement at low relative velocities can occur for all the partial waves, actually. Okay, so then using this, plugging this into this expression here, you'll find that this sigma v rel becomes something like sigma bar x to the 1/2. So it changes, this relative velocity changes into a scaling with x root pi for n equals -1/2, n equals 1, n equals, 0, n equals 1. So n equals 0, there's no x dependence in this thermally averaged cross section, and in the case of v rel squared being the leading term, then this is basically 6 some sigma bar on x squared. Here, this cross section has just been, there's some overall factor which doesn't depend on velocity, and then times the velocity dependence. Okay. So this just allows some useful approximation. Sorry, this is not squared. This is just x. Okay. So in the notes, I give some examples of particle physics models with this sort of behavior. Okay. Okay. Now I'll start. So now we have the Boltzmann equation, and we also have a useful analytic form, a useful scaling for our thermally averaged cross-section. And then now we can look at approximate analytic solutions to the Boltzmann equation, yeah? So now we'll substitute in sigma v rel. It's going to be sigma n x to the n. Yeah, this is the temperature dependence. I should say, let me make things a bit clearer here. So when you take this thermal average here, if you thermally average, let me see. Basically, if you just imagine you thermally averaged VREL, this gives you a factor of t to the 1/2. Yeah? This is how you can then see this scaling with x. Okay, so we'll have this, we'll assume this form of the cross-section, thermally average cross-section, and then our Boltzmann equation just becomes dy dx. We'll write it as negative lambda on x n plus 2, n plus 2. Y squared minus y equilibrium squared. Let me write x to the n plus 2 so that the people online can also see. Okay, and lambda we found before, we did all that work. M Planck, M. Now this sigma n appears because we've factored out the scaling with the variable x. Sigma n, and then g star s on g half star radiation. Okay? Y equilibrium is just given by factor is if you work it out, substitute in the formula I gave you for n in the non-relativistic limit and also the s, and then you can see that this this goes as some factor a x to the 3/2 e to the minus x, where a is basically 0.145 g over g star s. Okay, g are the number of degrees of freedom of the dark matter, and g star s the effective number of degrees of freedom for the entropy. Okay. Now, take this equation. We want to find an analytic solution, a good approximation. Yeah. We'll introduce the variable delta, which is just the difference between y and the equilibrium number density, normalized to entropy. Then, just rewrite this, and you should find that delta prime is negative y equilibrium prime minus lambda x 2 plus n delta plus 2 y equilibrium, okay? Primes just denote derivatives with respect to x, okay? At early times, when the temperature is large and the annihilation rate is large compared to Hubble, so between some value of x between 1, or in principle even higher, but we're interested in temperatures below the mass, to some freeze-out value, xf. We'll define this later. Both delta and delta prime are somehow small. Yeah? So you can see this, that when the annihilation rate is large, y is roughly y equilibrium. Okay. Approximately y equilibrium. And then we'll reach this value xf, and that's where the freeze out will occur, and delta will become sort of significant, okay? So in this quasi-equilibrium regime until freeze out, we're in this quasi-equilibrium regime where delta prime is approximately 0, and you have a balancing between these two terms. Okay? It's just the annihilations keeping y close to y equilibrium. And in that case, you have the relation that negative y equilibrium prime balances the annihilation, sort of the annihilation term, the rewritten annihilation term. Okay. And from this, we see that in this regime, until freeze out, delta is approximately given by negative y equilibrium prime x n plus 2 on lambda delta plus 2 y equilibrium. Okay, and now you evaluate y equilibrium prime, and you see there are two terms. One comes from the x prefactor, which just gives you 3 on 2 y equilibrium on x minus y equilibrium. Now, this is occurring roughly when this freeze out will be occurring when x is like 20 or 30 or something. So the second term dominates. Yeah? We're just interested in a approximate solution. Yeah? So we'll just take this to be approximately negative y equilibrium. Now we have this relation here. Yeah. Let's keep this. It's useful. Okay. And now we have to find what we have to estimate this x freeze out. The strategy is just to estimate this x freeze out and then substitute it in here. It's very sort of it's surprising in the end that the solution approximates well the numerical results. Yeah, with a bit of let's say fitting. Yeah. Okay. So we'll define. Okay. Yeah, I need about 5 more minutes. So it's okay. We'll define x freeze out to be when this value delta, which is the departure, sort of parameterizing the departure from the equilibrium value, when this is equal to some order 1 number times y equilibrium, okay? C is just some order 1 number, okay? Then from this here, we'll find that delta is then approximately, delta at x freeze out is approximately negative y equilibrium prime lambda y equilibrium c plus 2. So all I've done is substituted in this c and factored out the y equilibrium. Okay? And then in the numerator, we have this x, n plus 2. Okay? And we said here in the approximations we're using, y equilibrium prime is approximately negative y equilibrium. Yeah? So we just put a plus sign here and cancel these out. Yeah? And you think it's never going to work, but somehow it does. So then, okay. So then at freeze out, this has to be equal to c times y equilibrium, which is equal to c a xf to the 3/2 e to the minus xf. Yeah? Then we're going to estimate. Now we have this x freeze out in this exponent. Yeah? So then we have to estimate that. xf is then the logarithm of lambda c plus 2 a on xf n plus 1/2, which is then equal to logarithm lambda 2 plus c ac minus n plus 1/2 log of xf. And then we're going to just take this first term and just substitute it into here to improve to get a rough estimate. Let me keep that there. So now we have a formula for xf. And good, because then we're almost at the end. AC minus n plus 1/2 log lambda 2 plus c AC. Close this log and this one. Okay. Now we're going to cheat a little bit and set c plus 2. We said c is order 1, but now people, of course, have solved this numerically. So to get a good approximation to the numerical solution, it's useful to set this c plus 2 to be n plus 1. Yeah? And n, remember, comes from this scaling of the cross-section. Okay? So then we have here, then if we substitute this in to here, we'll have our value for delta at x freeze out. Okay? Now, after freeze out, delta prime is just equal to negative lambda x n plus 2 times delta squared. Unfortunately, you can see here. Unfortunately, I erased that, but when the y equilibrium part is not important, yeah? Just delta. And then you just take this, this is, I'll write this as d delta dx. Just take this delta across here, this dx across here, and then just integrate both sides, yeah? And you'll get 1 on delta xf minus 1 on delta infinity is equal to negative lambda on x n plus 1 n plus 1, okay? Okay. So we're interested in this value, delta infinity, which will be our number density of dark matter particles at today, normalized to entropy. And this is a standard sort of formula you see in the literature, but you can even simplify it a bit more by assuming that if you assume that delta infinity is much larger than 1 on delta at xf, this is delta evaluated at xf, and this delta when x is infinity, yeah, today. So you can just ignore this term, which is what we'll do, and then we find that delta infinity is just n plus 1 xf n plus 1 on lambda, okay? And xf is given by this formula here. And this is actually a decent approximation to the numerical solution. So let me just finish off by saying, yeah, okay. So then you substitute in and find that y infinity frees out is equal to xf n plus 1 on, I'm just substituting in for lambda here, m Planck, m sigma n, g star radiation to the 1/2 on g star s 45 on pi, okay? So this is now our result. And I should tell you that the observed relic abundance, so remember if x and x bar are distinguishable, we should multiply this by 2. The observed relic abundance just corresponds to the y dark matter, m dark matter, so this m is just m dark matter. If you want to compare this, what you calculate here, to the observed abundance, there's a very simple way. I'll just give you the result. This is equal to 0.43. I won't derive it here, just 0.43 EV. This is the observed relic abundance in terms of Y and M dark matter, okay? So you can see here, XF will depend only logarithmically on lambda, yeah? And so if you want to get the correct relic abundance, multiply this across this M, and you see it depends 1 over sigma n, and is independent of the mass of dark matter. And this is a standard result for this sort of dark matter freeze out. Yeah. So the standard you can check then to get the correct relic abundance you can check for this can be an exercise, just evaluating the formulas. Yeah, you have to do some unit conversions. Yeah, check that for sigma bar equals 2.2 times 10 to the power of negative 26 centimeters cubed per second. Set the m dark matter to be 1 TeV if you like. In GeV, this is given as inverse GeV squared. This is given as 1.86 times 10 to the negative 9 inverse GeV. And you can set, imagine you have a Majorana particle as your dark matter. Yeah, so that's in the indistinguishable case. You can set, say, G equals 2 and take G star S equals G star radiation to be the high temperature standard model values of 106.75. And you should see then, find XF, plug in the numbers, and you should see then that you get the correct relic abundance. Okay. So, very good. I should just draw a little picture. This is really the last thing I'll do. So the picture is the following, right? We have here yx. Here we have x. This is, let's say, 1 here, 10, let's say 30, and you had the, you have the equilibrium number density rapidly becoming Boltzmann suppressed, and then for the freeze out case, we had this, for until freeze out, x was tracking. This is yx equilibrium. It tracks yx equilibrium very closely, and then at well, we can extend this out a bit here to get the plot looking nicer. At xf around 20 or so, 25, 30, you get the freeze out, and this becomes constant. So this is exactly what we've solved, just in terms of this variable delta, which is yx minus yx equilibrium. So, sorry I went over a little bit of time, but hopefully you find this useful. Yeah, I should say, you get a similar estimate by just setting, morally similar estimate by just setting gamma annihilation equals to h as your freeze out criteria. This whole thing is just the same thing, just carefully done and a bit more precise, yeah? But because these Boltzmann equations often appear in lots of different contexts in cosmology, it's also just useful to look at this very simple example. Yeah. Thanks.
Thank you, Iason. So questions for Iason?
All these approximations work because lambda is huge, right? I mean, lambda is dimensionless, and it's a huge number, and that's why it works, no?
Yeah. That keeps you, large lambda keeps you in equilibrium for a long time, and yeah. And basically if you look at this, let me say it this way. What happens is you see at small x, y squared is close to y equilibrium, and lambda, here, choose the n equals 0. This doesn't even have an x dependence. But what really pushes you out of equilibrium, y squared is getting doubly Boltzmann suppressed. So this all of a sudden means exponentially, as a function of x, all of a sudden you drop below Hubble very quickly. Yeah.
Thank you. So in some point of your calculation, you consider the yield as divided by the entropy, right?
Yes, that's right.
Density and the entropy. So my question is, why the entropy and not just the scale factors to the third power or other quantity?
Yeah, it's a good question, and the reason is
because you want to factor out the redshift, right?
Yeah,
the expansion.
That's right. Yeah.
Why the entropy or no other intensive quantity, right?
It's because of these. It wouldn't make a difference if you didn't have these changing degrees of freedom. So this modifies the expansion a little bit, yeah, because
Okay,
so it modifies the relation between temperature and scale factor a little bit, because the temperature is falling a little bit slower than the scale factor when these degrees of freedom are changing. And then it's just convenient, because we know the observed dark matter density at matter radiation equality and so on, C and B a bit afterwards as well, to get everything to work.
I see.
It's useful, you know, here to find this value. I'll take, you know, you take G star S at matter radiation equality or whatever.
Okay, that's clear to me. Thank you.
So there's an online question, maybe related. Can you comment what kind of processes are neglected when you assume that no entropy is produced?
Yeah. So imagine you have, for example, a simple scenario. Let's say imagine your dark matter has already frozen out. Yeah. So then you just have a number density of dark matter particles, and the universe is still expanding. And now imagine you have a phase transition. Yeah. And imagine the easiest scenario to imagine to see how it works is imagine the phase transition is really, really strong, and we go into a vacuum-dominated regime. Yeah? In a vacuum-dominated regime, the energy density of the universe is constant, but the universe is still expanding. Yeah? The energy density is constant, and the universe is still expanding. So all your dark matter particles in that case are getting diluted with the scale factor. But eventually, you know, we have to re-enter radiation domination. So then we have to have a reheating process. And in this reheating process, you produce again a lot of radiation. And so your radiation density is again sort of the same as the initial radiation density when you enter the vacuum-dominated regime, because all the energy density is just change back into radiation. And then you can see that you have this massive expansion, but it's not taken into account. The expansion has to be taken into account in terms of the dark matter dilution. But if you just assumed constant entropy, this wouldn't work. So this reheating process, you know, your entropy density also gets diluted like the dark matter, but then you produce new entropy again. Yeah? And so then you have to factor in this new entropy production. So Yx equals Nx on S. So this, during this vacuum-dominated regime, say, this would all be constant. But then afterwards, you don't produce any new dark matter particles, but you produce a lot of entropy again. Entropy density again will shoot up. So then you have to take into account this production. So one possibility is a strong phase transition. You see it most easily if you get a vacuum domination, but even without vacuum domination, you always produce a little bit of entropy. And also another possibility is that you have an early matter-dominated epoch. Say you have some particle which is very long-lived, and it'll come to dominate the energy density of the universe. At early times, you'll have an early matter-dominated phase. This particle will decay eventually, and when it decays, it goes back into radiation, and there also you produce entropy. So you have to take this into account. And you can see that you'll have this, while the particle is, the matter domination is in effect, the universe, basically the energy density of the universe will redshift a bit slower than if it was radiation domination. And this is basically the whole thing, the entropy factor is useful sort of as an accounting measure for these additional expansions you can get if you change the equation of state.
Okay, so I'm sure there are more questions, but since we're a little late, let's leave the questions for the discussion session. And let's have half an hour of coffee break. I think it's important to relax. And also for the posters. So we get back at 5:15. So let's thank